Hello, my name is Olivia Killian. I'm 17 years old and from Maine South High School, and today I will be presenting iron and zinc regulation in plants when presented in excess amounts. But firsthand, I would like to thank Ms. Kay Wagner and Ms. Dawn Maiwinga for their guidance and for providing me with the necessary resources and encouragement. Mineral deficiency is something that I was very familiar with as a casual gardener, and deficiencies can manifest themselves in often like discoloration of the leaves, as we can see in the photo here. But this led me to wonder what would be the effects when these are presented in excess. If someone happens to over fertilize their soil and now there's suddenly a toxic level of these minerals in the soil. So for this experiment, I used the University of Madison-Wisconsin fast-growing plant. I used the rosette dwarf variety as they had thicker, wider, flatter leaves that sprouted closer to the soil compared to the standard variety that had a little bit of a lighter coloration, didn't sprout nearly as close to the soil. And these plants also have they germinate at a much faster rate compared to normal plants, which was perfect for the time constraint of this experiment. So, for some background on iron's relationship with plants, so iron is uptaken through the plant by its roots using reducing and chelating. So, chelating occurs when the plant releases phytosiderophores, which are small, minute plant extracted organic molecules that have a high compatibility for iron, while reducing is characterized by a release of plasma membrane protons to lower the pH levels in the rhizosphere. This is commonly known as acidification. And absorption modifications are needed to prevent toxic levels of iron absorption from penetrating the plant tissues and potentially being very harmful to the overall system. And physical indicators of iron toxicity can be chlorosis or yellowing of the leaves, faulty root growth, overall lowered mineral absorption, and even development of iron plaques or buildup in the rhizosphere, which is again the environment surrounding the roots. So a diagram on iron chelating, you'll have iron present in the soil, the chelating agent is released, and then iron is able to be uptaken by the plant through its roots. Um, so with zinc, this can occur, high levels of any mineral can occur in soil due to either chemical or physical erosion of rocks, called calamine soils, or just soils that have high levels of minerals. Similar to iron, zinc, excess levels of zinc can appear can have physical symptoms of root apex necrosis, chlorosis of the leaves, bronzening of the leaves, curling of the leaves, and deduction in leaf size. Something to know is that grass species are usually less responsive in acidic soils compared to dicots or flowering plants, and this is perfect because the rosette dwarf was a flowering plant that I was using for this experiment. So my hypothesis was if a University of Madison-Wisconsin fast-growing plant is exposed to an excess of ferrous sulfate and zinc sulfate through contamination of the soil, then alterations to the regulatory processes of these minerals will manifest themselves in the discoloration of leaves, root necrosis, decelerated rate of growth, and lowered pH levels in the soil. So for my experiment, I assembled 14 pots, two control pots, and then two pots for each of the different concentrations. I had a concentration 5 times the ideal amount, 10 times the ideal amount, and 20 times the ideal amount for iron and zinc. So initially, I tested the pH level of the soil by mixing in a small amount of soil with water, agitating it, filtering it, and then testing the filtered water with a pH strip. And then I had to calculate the recommended amount of ferrous and zinc sulfate, which was much more difficult than I anticipated because there wasn't much research on the ideal amount of these minerals for the specific variety of plant that I was using. But I cross-referenced and got a general estimate, and then I multiplied that ideal amount by 5, 10, and 20 to get the excess concentrations. I mixed in these measured elements into the soil along with a generic fertilizer that was provided with the University of Madison-Wisconsin plants. And I place these seeds into the pots a quarter to half an inch from the top of the soil. In this upper left-hand corner photo here, these are my 14 pots. To the right of that is the measured elements that I introduced to the plants, and then below that is the filtration process when I was testing the pH level of the soil. I would water the plants daily with 15 milliliters of water, and throughout the process, I would photograph and observe the characteristics of each of the plants, including the root length, coloring, and overall growth, and then I would test the pH levels of the soil every 30 days. So on the 30th day, I had some very puzzling results. Um, so the photos or the pots furthest away from the camera, which are the 20 times the ideal concentrations, are actually seeing overall increased growth compared to the control, and even the 5 times the ideal concentration. And I was seeing full and healthy leaf growth. So I was wondering why I was actually seeing increased rates of growth when I was anticipating that there would be deterioration and or overall maybe a lack of germination to begin with. But then I start to suspect that possibly there were some alterations being made uh, to the concentration levels that I had measured because there is filtration or drainage holes at the bottom of each of the pots, and the water was pooling at the bottom. So I was suspecting that the concentrations were being altered. So on the 30th day, I reintroduced the calculated sulfate amounts and reintroduced them to the plants by creating a solution with 15 milliliters of water. As you can see with the photos, we had full healthy leaf growth and even flowering. So on the 60th day, the results were much more what I was expecting. So in this upper left-hand corner photo here, you can see chlorosis and deterioration. And this was an iron 20 times the ideal concentration plant. And below that is the control. So you can see the control is consistent coloring and no signs of deterioration. And to the right of that, we can see the control group is furthest away from the camera, and that is very full, healthy growth, while the 20 times the ideal amount, they have very thin, frail stems, and only two of the seeds were germinating. And I also saw a slight lowering of the pH levels from roughly 7 to 6. So for the data, the average growth of the control plant was just shy of 12 centimeters, while the average growth of the zinc and the iron trials were roughly 9 to 10 centimeters. So there was about a 2 centimeter difference between the exposed plants. And there wasn't conclusive evidence to prove that the soil had decreased just because it was hard to measure accurately just with simply the pH test strips. But I did see some slight lowering in pH levels. So as you can see, we actually saw initially increased rates of growth in the plants that were exposed to presumed toxic levels of iron and zinc. But after the reintroduction on the 30th day, that is when the control group passed the exposed plants in growth, and the control did not display any yellowing. It is also worth noting that the control groups, all 4 seeds germinated, while only 2 to 3 seeds in the altar pots germinated. And this leads me to believe that possibly the concentration that the plants were initially exposed to more likely represented an isotonic or hypotonic environment, which is an environment that plants thrive in. When I was trying to create a hypertonic environment, which is where the solute level in the environment outside the plant is much higher than the solute level um, inside the cell. So my hypothesis was correct in some aspects, but it was also incorrect in other ways, which I thought was interesting. Some possible errors is that, again, there was pooling and contamination of the water. There's also pilder or powdery mildew growth on the plant seen on the 60th day, which is an indicator of a high humidity environment. So possibly the plants were in not an ideal environment to begin with. I also wanted to measure the root growth throughout the process, but soon I realized the roots were too delicate to be removed without breaking or disruption. The seeds could have also been pushed too far under the soil, which could be due to any lack of germination. And I also had a small sample size due to lack of resources, so it's hard to come with a definite answer when you only have so few trials for each of the different concentrations. So the experiment proved and disproved some aspects of my hypothesis. The zinc and iron plants did exhibit leaf discoloration following the reintroduction on the 30th day, while the control did not. Also, the decreased pH levels were exhibited in especially the 10 and 20 times the ideal amount concentrations, and my initial calculations for trace elements actually seemed to encourage growth. So this leads me to believe that the Madison-Wisconsin plants thrived in slightly higher concentrations of zinc and iron sulfate during the early stages of growth, but once the plants became acclimated to the soil and the high concentrations were then introduced again, this is when the symptoms of chlorosis and deterioration began to manifest themselves in the plants. Thank you.